studying error correction and sort of physical ion trap error models. And before that, I was an undergrad at East Santa Barbara. So this talk, in terms of general, is like kind of pretty vague, not vague, but pretty general. It's not specific to what we're doing at Google or anything specifically about that. It's mainly going to be basics of quantum computing, sort of like what the fundamental components are, how the information is used. Then we're going to go over a basic quantum algorithm. So I know there's like sort of a wide range of audience knowledge levels here. So hopefully everyone will have something to get from some part. But there's going to be a sort of intro to quantum stuff, then an algorithm, and at the end we'll talk about error correction for a bit. So for those of you who don't know what error correction is, we'll get into that. But essentially, it's a way that we hope to make these quantum computers reliable in the long term, and most of us believe will be necessary for large-scale quantum computation. So if it's just you guys get a flavor for that as well. But yeah, with that, I'll get started. I have the chat open, so if you have questions, you can type in the chat, and I'll try to answer them within sort of the rhythm. Okay, so first I want to start with a bit about what quantum computing isn't. So there's a lot of hype about quantum computing right now. It's a very buzzy field. There's a lot of interest, and a lot of that leads to claims being made that are not exactly reasonable, or put a lot of undue pressure on the field in ways that we don't, as a field, believe we can answer for. So as a sort of entertaining example, there's this headline that came out from Vice talking about a complexity theory proof that came out, where they used the headline, "Mathematicians are studying planet-sized quantum computers with godlike powers." So there's very little we can do to quell the hype, but just sort of explain some things that come out of this. I want to shoot down a few claims that aren't true, or that don't really get to the point of what quantum computing is. So firstly, quantum computers will not replace classical computers. These are where the machines we're trying to build are very powerful, but they aren't strictly better than classical computers in all tasks. So for example, multiplying two numbers is much easier on a classical computer than it is on a quantum computer. And with all the extra work you have to do to build the quantum version, it's just not worth it. So things like basic arithmetic, we should never be doing on a quantum computer. Similarly, certain reliability tasks, like quantum computers are intrinsically noisier. So we don't anticipate these devices to be on your phone or on a laptop. Maybe maybe in 100 years I'm wrong, but as of right now, these are very sensitive objects. So we aren't trying to make the next quantum everything. These the phones and laptops we have right now aren't going to be junk in 20, 30 years, we expect. Secondly, quantum computers will not in the next 10 years, though, break all of cryptography. I know this is sort of like one of the big selling points of quantum for some people is we can break RSA encryption, but we simply aren't there yet in terms of scale. Hopefully in 10 years, 20 years, 30 years, we're building these systems, and we have, Google has published a roadmap recently that shows kind of how we plan on getting to these larger problems. But in the short term, we still have work to do before we can get there. And then lastly, this is sort of just a pet peeve of a lot of people sort of in the field. Quantum computers do not work by testing all possibilities at once. That's definitely part of it, that there's parallelism and superposition are important parts of quantum computers. But there's sort of this notion, especially amongst sort of things that try to explain quantum computers in a very basic, easy way, where they say basically that the entire speed up comes from parallelization. And that isn't really true. That's part of it. I'd say the fact that you can parallelize things and then have them interfere in interesting ways is what really gives our quantum computers the power that they have. So with that, I want to sort of give a bit of a roadmap of what applications we can reach. So this is a few years old. It's from this paper on the bottom here, 2018. But this sort of shows you the kind of error rates, qubits, y-axis, that we'll need to hit certain algorithms of interest for our field. So, for example, this red blob here is a Heisenberg simulation, or blue diamond here is a Shor's algorithm implementation. You'll notice there's two bluer regions. there's a FT sort of region here and a NIST region here. What those two stand for is FT is fault tolerance, that's with error correction, and NIST is always. And so what that means is that for these algorithms, we need a very, very low error rate. And so we can either make our errors incredibly low and build a very, very reliable computer. And then we only need 10 to the minus, or 10 to the 3, 10 to the 4 qubits. Or we can use error correction, which is a way that I'll talk about later for us to use redundancy to minimize errors. And what that allows us to do is to trade space, like, qubit size versus gate error. So we can handle noisier qubits if you can give us some redundancy that we can work with. So I'll talk about that later. But here are some useful applications for our, so we can simulate quantum systems. That's the original sort of reason for quantum computation. Feynman had a quote that was basically saying, if you want to simulate nature, if you want to understand nature, you need to do it on a computer that's fundamentally quantum mechanical. And the reason for that is that it's very difficult to describe objects on a classical computer or in a class thing. And so if you build fundamentally quantum parts, it's a much more native translation. And that allows our computers to be really good at like spin chain Hamiltonians. Secondly, as mentioned, factoring numbers is one sort of application that people are pretty excited about. And then lastly, quantum encryption and communication, which I'm not really going to talk about in this talk today. Basically, you can create sort of protocols that use the fact that quantum objects you can tell if they've been measured in order to send messages that are not susceptible to certain attacks that other encrypted messages might be. But that's a bit out of the scope of this talk. So with that, I'm going to quickly start with the building blocks of quantum computation. So we store information on a quantum version of the bit called the qubit. So the standard bit is either a 0 or 1. On a hard drive, it's stored as either like a high voltage or low voltage, or depending on the type of hard drive you're using. Our bits are two-level systems, quantum two-level systems. And so they can use the standard quantum phenomena of superposition and entanglement. And so I'll explain what those are in the next few slides, but essentially taking advantage of these sort of quantum mechanical properties are what give our computers their power. So we use the interference of these quantum states. We use the sort of phenomena that quantum mechanics gives us to create a richer set of algorithms we can implement. And then here on the bottom, I have a picture from one of our older devices at Google Quantum AI. This device is called Foxtail. And so you can see it's a 10 by 2 array of qubits. And so one thing I want to point out here is that most of this chip and most quantum computers are control electronics and things that are not the actual qubits themselves. So that's true of classical computers as well. But the qubits are just these guys right here. That the qubit's like a small bit of that. And the rest of this is all like readout lines, control lines, etc. In that picture I had in the beginning of my first slide, that huge assembly is mostly control electronics, and there's also going to be a fridge built around it to make these things cold. The actual chip itself is very small, and most of that machinery is just to control it and allow us to really precisely read out measurement and observe what's happening on the chip. So first we want to talk about qubits. Qubits are two-level systems I mentioned, so we'll describe their states as 0 and 1. For those of you who haven't seen it, this is Bra-Ket notation. So a quantum state will be defined by one of these sort of objects with this bar and this angled bracket. So the state 0 we will label as such, and then the state 1 will have a 1 instead of a 0 there. And then any quantum state can be described as a superposition of different states. So 0, 1 is a basis for our two-level state space, and then you can apply any coefficients alpha and beta, complex numbers, such that alpha squared plus beta squared is equal to 1. And then if you measured this qubit along the z-axis, which is the 0, 1 basis, you would have an alpha squared probability of being 0 and a beta squared probability of being 1. So this restraint essentially is saying that your probabilities add up to 1. So as I mentioned, classical states are 0 or 1 discretely. So basically, on this large sphere, those two states are this top state or the bottom one here. However, a qubit can actually occupy anything on the surface of the sphere. So you can see there's obviously a much richer space of states we can work with. And so that's one thing that sort of gives our quantum bits a bit more power and a bit more control, right? They can describe superpositions. So I can have a 0 plus 1 state, as shown here. So superposition is the quantum mechanical principle of a state being essentially probabilistic in some way, right? There's some it's in a state that is between two others, and when you measure it, you can project it into one side or the other. So the way we describe that is by putting certain coefficients here. So here my alpha is 1 over square root of 2, and beta is also 1 over square root of 2. And what that gives us is an even superposition. So if I measure this, I'll get a 50-50 chance or a 0 or 1. So this is a state that a classical computer cannot describe on with a single bit, right? Like it needs to describe a little bit of a larger object in order to fully describe a quantum bit. And that's one of the reasons that simulating classical computers is so hard, is that to simulate a full quantum computer with n qubits, you need to store a matrix, or to store that piece of information, you need to store a matrix that's 2 to the n by 2 to the n, the density matrix of that state. And obviously that's going to scale exponentially with the number of qubits. So this is why classical computers take an exponential number of resources to simulate a quantum computer, essentially because our classical bits cannot properly describe a quantum bit efficiently. So superposition is sort of where that running all possibilities at once language comes from, because quantum objects are linear. So if I apply some operation to the state, let's say I apply a Hadamard to the state, I will apply a Hadamard gate to the 0 qubit and the 1, or the 0 state and the 1 state independently. And then they'll both transform as if they'd undergone that operation. And so you can have sort of you can imagine sort of multiple threads or whatever operating at once. However, when we measure, we will only get the outcome from a single one. And so that's sort of where the difficulty comes in, is that you might have a lot of information stored in your superposition, but measurement collapses it. And that's where we sort of have to bring the quantum information back to the classical realm before we can understand it. So the more sort of famous quantum, I guess phenomena is entanglement. So quantum entanglement is a system, or is a situation where two quantum objects can be put into a state such that they no longer can be described independently. So in this example here, I have a state 0, 0 plus 1, 1 over square root of 2. And this state cannot be factored, right? Like I cannot ask the question, what state is qubit 1 in? Because the state of qubit 1 is intrinsically dependent on the state of qubit 2. They're essentially fundamentally like a 4-level object now. And this is not something we see with our classical bits. So if you give me a bit string, 0, 1, 0, 1, 1, each individual bit is in some state. So I could store that information. So basically we only have 5 2-level systems. In a quantum setup, we can store states that no longer can be factored and separated. And as a result, we sort of exist in a natively 2 to the 5 level system for that 5-qubit system. And so this is sort of what gives us a lot of power, right? This is what makes our qubits able to encode so much information. They can explore states that classical computers cannot. And using entanglement, we can have really powerful sort of states that can encode information in very clever ways. And that's sort of what I'll show you in the algorithm we discuss in a few slides. So as I mentioned, these states can't be separated. And the first visualization of that came from this paper here in 2019, where they created these entangled pairs of photons and they measured them along different axes. And they applied a force to them such that their state led to different positions along some measurement axis. So what they did is they created a state that's equivalent to 0, 1 plus 1, 0 in our quantum computing language. And they measure them, you can see that they always got these 2 even clouds on their measurement apparatus. So that means that in every single run, when they measured the 2 photons, the photons were split. They always went in opposite directions. But on average, each photon could be in 1 or 0, could be up or down, diagonally to the left or diagonally to the right, etc. However, so nature sort of didn't know which one was going to come out, but it did know that they're going to be in opposite directions no matter what happens. And this is kind of the quantum sort of entanglement setup. I could take this 0, 0 plus 1, 1 state, give my friend one of my qubits and walk away. And if I measure my qubit and it's in 0, I now know that his qubit is also going to be in state 0. However, if I did that over and over and over again, and I measured 1 on occasion, I would sometimes get 1 on the other side as well. It's not defined as 0 or 1. It's just that it's 0, 0 plus 1, 1. So whatever I get, he's going to get as well. Okay, so with superposition entanglement, we now have sort of some of the building blocks of these quantum objects. However, we still need to do things to them, right? How do we create a state 0, 0 plus 1, 1? So the way that most quantum computers work, they start off in some fiducial state that's known, which is the sort of like initial state. So for our quantum computers and most in the field, we start out in the state 0, 0, 0 for all qubits. But then we want to create some interesting quantum algorithm, and we need to do that using gates or operations. So in the classical world, like you might know some gates like the AND gate, the NAND gate, XOR, etc. In the quantum sort of world, we have gates that are similar to those, but this is sort of a set that I want to explain because it's like a very basic set of gates. So you have a Hadamard. This is the X to Z basis transform. So the Z-axis here is this vertical axis, it's the 0 and 1, and the X-axis is here. And so 0 is going to be mapped to 0 plus 1, and 1 is going to be mapped to 0 minus 1. So essentially, in quantum computers, these phases are sort of where you are along this azimuthal angle, and we're going to basically flip the Z-axis and the X-axis. That's what we're doing with this Hadamard operation. Polyrotations are very simple on this picture. They're just rotations about the different principal axes. So you might have a small angle X rotation that rotates the state psi to some state over here, or so on. And then lastly, you have a 2-qubit operation, the controlled knot. So this is called a C-knot as well. And what it does is it applies a NOT gate, an X rotation, to the second qubit if the first one is in the state 1. So a C-knot on 0, 0 will go to 0, 0. A C-knot on 0, 1 will go to 0, 1, right? Because this first qubit's in 0. But if this first qubit is 1, 1, 0 goes to 1, 1, and 1, 1 goes to 1, 0. So the important thing with the C-knot is that it's an entangling gate. So it allows us to create entanglement between different qubits. So to create the 0, 0 plus 1, 1 state I talked about earlier, which I said was an unfactorable state, you would prepare 2 qubits in 0, and then you'd apply this Hadamard operation to the first qubit. So you now have the state 0, 1, or sorry, 0, 0 plus 0, 1, or sorry, 0, 0 plus 1, 0, I guess. You then apply a control knot, and the 0, 0 state will stay the same, but the 1, 0 state will go to 1, 1. And so you'll now have this 0, 0 plus 1, 1 state that you can't take apart anymore. So if you wanted to understand exactly what state that was, the best way to do it would be to actually invert that operation, apply another control knot and another Hadamard gate, and then you'd be able to measure it and see that you were initially in that 0, 0 plus 1, 1 state. But if you had measured it, directly, you would have gotten a 50-50 chance of 0, 0 or 1, 1 separately. So these are our sort of fundamental operations. They're the only ones I want to use for my for the algorithm we're going to talk about, and they form a universal basis. So every quantum operation you can imagine on any number of qubits can be created with just these fundamental pieces. So if you have control knots, if you have arbitrary angle rotations at single qubit axes, and a Hadamard, or you don't even need a Hadamard, really just these two here, you can get to any unitary you want. So any state can be created, any operation can be created, etc. So we focus in industry and academia everywhere on finding qubits and finding systems that can create these particular operations or equivalent operations. And by doing that, we know that we can get to whatever place we want to get to. So with that, I'm going to start on algorithms. If there's any questions about the first part, let me know in the chat. But my goal with this algorithm is not to show you anything particularly useful. This is a pretty toy problem example, but it's to get a sense for what is sort of happening under the hood when a quantum computer is running an algorithm, and sort of to understand a bit about the trends of how quantum algorithms, what kind of information they give you and how they work. So the algorithm we're going to look at is the single qubit Deutsch-Je algorithm. It was originally discovered in 1992. And it works for a lot of number of qubits. I'll talk about that at the end, but this is the simplest example. So first imagine a classical problem, right? Imagine I have a coin and it's either a fair coin, heads and tails, or it's a trick coin, like a rigged coin. And so it's either heads, heads, or tails, tails. And your task is to figure out whether I have a real coin or like a fair coin or a rigged coin. And the way I let you do that is I give you a function f of x, where essentially that corresponds to looking at a side of the coin. So you give me an input, either 0 or 1 for like the first side or the second side, and I will give you an output of either 0 or 1. So f of x takes 0, 1 to 0, 1. And you want to find out whether or not this coin has 2 heads, 2 tails, or heads, tails. So the classical algorithm is, very intuitive. You guys all figure this out. You first look at one side of the coin, then you look at the other side of the coin. And if they agree, great, it's a trick coin. If they don't agree, it's a fair coin. This is very easy. And the key thing to see is that we needed to look at 2 queries to our initial function in order to figure out if this coin was fair or rigged. So you had to look at one side and then the other. Before you looked at the other side, you had no information about the coin's situation. And then also note that once you do solve it, if the coin is rigged, you'll know if it's rigged towards heads or towards tails. So you get some information for free at the end there. What we're going to see is that in the quantum case, that doesn't happen exactly. So let's translate this into a quantum problem. So someone gives you a coin or has a coin, and you're told the same thing. You're told it's either heads, tails, heads, heads, tails, tails. Now, instead of giving the function f of x, they give you a black box. So a black box is a sort of like a function in a quantum system. It's a operation or a gate or a circuit that you don't really understand. You're not told the internals of, but you can feed in things and get outputs from it. So in this case, the black box they give you takes in 2 qubits in 2 states we're going to call x and y, right? So these could be x and y, could be any state. They could be 0, 1, some superposition of 0 and 1, etc. But they're just 2 single qubit states. And what they output is the same qubits in the states x and y o plus f of x. So what this o plus is addition modulo 2. So if you imagine this y is in the 1 state and f of x is 0, you will get 1 again. If this state here is in the 1 state and this is also 1, you will get 0 back out. So basically it's 1, it's like, x plus y mod 2. So 0 plus 0 is 0, 1 plus 1 is 0, 0 plus 1 is 1, 1 plus 0 is 1. And your task is, again, to figure out if the coin is fair or rigged. So to solve this reframe problem, which is basically just a quantum version of the classical one, with a quantum computer, we will do the following thing. We'll first prepare the states plus and minus, right? So 0 plus 1 over square root of 2 and 0 minus 1 over square root of 2. And those will be our x and our y. We're going to feed that into our black box object. And we're going to end up with a state that's going to encode the information we want in a relative phase. And then what we can do is we can measure that qubit in a specific basis and get our answer all in one circuit execution. So that's the big sell, right? Is that we can do this whole thing with just one query to our black box, as opposed to the 2 queries necessary for the coin on a classical case. So this is a bit abstract. Let's look at it in math. So this is probably the most mathy slide in this talk. But I've tried to color code it so it's not too intimidating, hopefully. I've also gone away with all of the normalization factors because they're just going to add to the complexity. But there's a 1 over 2 basically over the whole thing until the end. So we started out with our state x, y being equal to 0 plus 1 and 0 minus 1, right? So then we can distribute this out. And specifically, we can distribute it in this way, where we distribute 0 times 0 minus 1 plus 1 times 0 minus 1. Now, the reason I've done this is because when the black box takes in each of these individual sets, these 2 are going to behave the same, are going to have the same thing applied to them because f of x will be the same. And these things are the same thing applied because f of y is the same. X is the same again. So we now pass this to our black box, and we end up with the state 0. And this will be multiplied by 0 plus f of 0 minus 1 o plus f of 0 plus 1, 0 o plus f of 1 minus 1 o plus f of 1, right? So this is the exact operation of the black box I talked about earlier. If you want to see this yourself, you can distribute out again to have 4 individual pairs, apply the black box, and then refactor it into the form I've shown you here. So the reason I've done this is because we now can understand what this operation does with a function that only has values 0 and 1. So if f of 0 is 0, what's going to happen, right? This 0 is going to be 0 plus 0, still 0, and 1 will be 1 plus 0, still 1. So you'll get the exact same operation out, right? So essentially, if f of x is 0, then this state is left unchanged. However, if f of x is 1, right? So f of 0 is 1. 0 plus 1 is now 1. And 1 plus 1 is now 0 because of this mod 2. And as a result, we've gone from 0 minus 1 to 1 minus 0, which essentially is a phase of 1 or minus 1, right? Like you've had a minus 1 factor multiplied to your state. And so what the black box essentially is doing with this particular special input state is it is applying a phase of minus 1 to your state if the function f of x evaluates to 1. And so what I do then is I can write this out in this weird sort of form where I sort of encapsulate that into math by saying it's minus 1 to the f of x, or to the f of 0, and then minus 1 to the f of 1. So I've now encoded that relative phase information into these two states here. Is there a question? Sorry. So someone's like name light up, but I'm not sure. Okay. I guess not. So we now have these two phases that have been applied based off of what the functional value was for the states 0 and 1, respectively. And then the last sort of trick to this algorithm is we're not going to measure in the z basis. So we're going to only measure the first qubit. We can throw the second qubit out for now. We're done with it. But what we're going to do is we're going to measure it in a special basis, the x basis, which differentiates not 0 and 1, but 0 plus 1 and 0 minus 1, right? So keep in mind that in quantum systems, a global phase is sort of invisible. Everything's done up to a global phase. So you can't tell if the state you have is 0 plus 1 or minus 0 minus 1. Those two states can't be told apart. What you can do is you can look at relative phases. So essentially, if the qubits, if the function is constant, right? So if f of 0 and f of 1 are equal, let's say if your coin was a trick coin in the questions language, then these two phases will be the same. Either they'll be both minus 1 or they'll both be plus 1. And you'll end up having a state that is 0 plus 1 multiplied by some phase. However, if the coin is fair, one of these two will be minus 1 and one will be plus 1. So you either have 0 minus 1 or minus 0 plus 1. And the relative phase will be minus 1. So what this x basis measurement is doing essentially is measuring the relative phase between 0 and 1 and telling you whether it's positive or negative. And as a result, in a single measurement, we can find out if the sides of the coin match or don't match. And in a single execution of our algorithm, we will know if the coin was fair or rigged. So this is like probably a pretty complicated point. So I'm looking at questions. Can I explain the exponent again? Yeah. So what this exponent essentially is doing is just encapsulating this sort of special input state structure. So if your state y is this particular 0 minus 1 state, then when a function f of 0 is added to both sides, right, it's going to do different things depending on whether that f function is 0 or 1. So if it's 1, it's going to essentially swap the sort of initial 0 minus 1 state into a 1 minus 1 state. And if it is 0, then it's going to leave everything alone. So I'm just this exponent is just me encapsulating that into sort of a single compact form. So essentially, if f of 0 is 0, everything's left unchanged, and this overall exponent is just going to be 1. And if f of 0 is 1, this overall thing will be minus 1. And f of x itself was that sort of black box I had earlier. So let me go back one. So here, f of x essentially is just some function that tells you what the face that particular face of the coin is. So if I feed in 0 as x, what f of x is telling me is whether the 0th side of the coin was heads or tails, where we can say like heads is 0 and tails is 1, for example. So that's just the function that tells you about your coin. And we're going to encode its information into a relative phase by using this particular input state of 0, -1. So this is an idea called phase kickback, if you're a bit more of an algorithmically inclined person. But yeah, so using this in a single execution, we can understand whether the coin is a trick or fair. And this is a very simple demonstration of sort of this quantum advantage, like a way that a quantum computer can be faster than classical and feasibly. So we were able to solve the problem by using superposition. And the important thing is that actually this problem, as you scale up, it gets even better. So imagine you had a n-sided die where like n is even. So you can see like a 32-sided die where you have 16 zeros and 16 ones. And your goal is to find out whether you have a fair die, which is 16 zeros, 16 ones, or you have all zeros or all ones. Well, the algorithm is very simple on the classical side. You look at one side, you look at the next side, look at the next, and you keep doing that until you either don't have them match or you have more than half of them as 0 or 1. If more than half of them are 0 or 1, you know that you have a rigged die. And if you have a 0 and a 1, you know, oh, great, they're 50-50. So as you get a bigger and bigger die, you will need more and more looks at the die in order to find out what happened feasibly. In the quantum case, you can always do it in a single execution. So no matter how big of a die, no matter if you have a 20-sided thing, whether you have a 2 to the 20-sided thing, it'll always take a single application of your black box in order to find out whether or not your function was fair or balanced or unbalanced. So that's nice, right? So that shows you a better scaling. So that's why this quantum algorithm is better. However, it does give us less information in the end. Generally, like I would say a big part of quantum computing and making algorithms is finding like a really good question to ask the state in the end. And oftentimes we will get less information from it than a classical one, right? Because the classical state, you measure it, you take some information out of it, and then you can go back and look at it again, right? You can keep looking at it. Here, we could only ask whether they matched. We couldn't ask what the two states were. And as a result, we don't find out in the end which direction the coin is rigged to. So the classical algorithm, if you give me a rigged coin, I look at it heads, heads, I'm like, oh, this coin is rigged towards heads. The quantum algorithm will only know they match. And that's kind of a key point, that we get very minimal information out of these quantum systems unless we repeat the algorithm multiple times. And then lastly, the effectiveness comes from looking at the information on a different basis. Oftentimes in quantum computation, we get a lot of our power from the fact that our qubits now have much richer spaces. So the fact that we can look at a relative phase basis or a direct 0 + 1 basis, et cetera, gives us a lot of the power in algorithms. And then Andrea asks, what is the black box? How do we get it if we build it as a black box? Right. So this is a good question. In general, black box algorithms are kind of unsatisfying. I think it starts when you learn them because, as you're saying, if you want to implement this in a system, well, why you're implementing yourself? Why do you have a black box? The idea is that, well, in a lot of algorithms, there's sort of a communication aspect, right? So you can imagine, for example, this sort of coin flipping thing, right, where the person who has the coin is the black box, essentially, right? So similarly, on a quantum setup, you could imagine having it where you don't know what's happening in a certain, someone else has a second quantum computer, you send them quantum question information, they do something, they give it back to you. So they might know what it is, and you need to figure it out. Also, I'd say in general, this particular example is a bit of a sort of toy problem to prove that you can, under some circumstances, have an algorithm advantage. I don't think, for example, this Deutsch-Je's algorithm itself will be particularly useful because, as you're saying, if someone else is throwing this weird function, you're not really too bothered whether you know it or not. But things like this can be used to learn about what someone else is running on their system. So you can probe a system of interest more efficiently on a quantum computer because you can probe it in different ways than you can on a classical one. But yeah, when you implement this right now, if I went on our computer right now at Google and wanted to run it, I would have to myself feed in a black box, and so it would be kind of a circular logic. But it's more of a educational tool, I'd say, at this point. So hopefully this was a relatively followable example of an algorithm. I know that it probably was a bit fast. I mean, quantum computing is a bit hard to learn in 45 minutes, obviously. So, but hopefully it gives you some intuition for how we use these systems, right? So we did use superposition by creating this crazy state. And then so this state is entangled, depending on the black box you have. But then a big part of it is that sort of as you go back and you interpret this in terms of this relative phase, you can actually apply another Hadamard, and you see that the reason we can sort of encode this is because there's interference happening. So the reason like the higher level system works is because when you revert back the measurement, you're essentially having different possibilities interfere. And so if you really take this thing apart and like go into the hood, there is interference happening as well. Without it, you wouldn't have this particular algorithm working. But yeah, in the last like 10 minutes of this talk, I think I have, or like 15, we'll see. I want to explain how we're going to actually make these things work, right? So I've sent you an algorithm. It was a simple one, granted, but it relied on the exact thing I wanted to happen happening every time, right? Like I say I want to feed in this state, and I need to feed that state in order for this to work. Similarly, when I applied a measurement or when I applied this black box, I needed to do exactly what it said it was going to do every time. And if it doesn't, well, I'm going to have a hard time figuring out what's going on. So that's why we need to reduce noise in our system. However, quantum computers and everything is pretty noisy. And so quantum error correction is really the art of making reliable systems, from noisy parts. So if we have qubits that have some noise, how do we deal with that, right? So first, I want to explain that there is noise in both the classical and the quantum worlds, right? So quantum computers are definitely noisier, but classical computers do things that we don't really think about, but it's insane when you think about like how much noise they must be experiencing, right? So when I like call somebody on my cell phone, I'm sending some zeros and ones encoded into some frequency at like a satellite, which is going to just translate another satellite, which is going to do something else and do something else and get back to somebody. And I get annoyed if I say something to them and they can't hear it, right? Like we have a rover on Mars sending information back to Earth, like 4K video. And that's like a ton of information traveling a very long distance. So some of it's going to go bad. And that's when classical computers use error correcting codes. So quantum computers are a bit more fragile. So on your classical computer, like generally, if it's just sitting there, you're pretty confident it's going to continue doing the right things. Quantum computers don't have that privilege, right? Like if somebody coughs in the room one over, our computer is going to feel it. Like it's just, they're very, very intrinsically noisy systems, because if you think about it, right, a classical computer, a 0 versus a 1 is like thousands of electrons being one place or another, right? If one of them hops over, it's water off your back, no one cares. But a quantum computer could be a single pair of electrons on this side or this side. And so any minute field difference or anything could cause a group pair to shift, could cause, a supercurrent to flip. Like our devices are superconducting qubits, right? And super squids, or superconducting quantum interference devices, can be used for all sorts of very, very high precision sensing technology. So I know there's a military application where they put squids on a plane and they could use it to identify submarines below the ocean surface. So if your object is that sensitive, well, then it's very sensitive to like unwanted noise in your environment, right? And that's what we're trying to fight with. So Shor's algorithm, as I showed you earlier, requires error rates of 10 to the minus 10. However, our modern experiments are around 10 to the minus 2. So we need to get 8 orders of magnitude reduction in our error rates, which are like the failure rates of our components, in order for things to work. So obviously, experimentalists are going to make improvements. We have incredibly talented experimentalists all across the field. These systems are getting better and better and better, faster and faster, getting bigger, et cetera. But 8 orders of magnitude is a large ask. And we don't fundamentally think that we're going to be able to get all the way there with just improvements to our physical experiments. We also need to bridge the remaining gap by, through theory, through like ways of making robust systems. And so what error correction does is it redundantly stores information in order to make these robust logical qubits, we call them, which are basically qubits that are composed out of a large number of physical qubits at the ground level. So first, to do this, I'm going to explain classical error correction. It's a bit more straightforward. And then I'm going to explain the translation we need to make into a quantum system. So first, we're talking about error models. We're talking about error correction. We want to talk about error models, right? So what does the error look like in our system? So as I mentioned, classical information is stored as zeros and ones, and your computer has large binary data streams. And the main error you see is bit flip noise. So a 0 goes to a 1 or a 1 goes to a 0. There are other noise models, erasure, etc., but this is a very simple one I'm going to talk about today. So the way this works is that when you pass some classical messages through a noisy channel, there'll be some chance for each bit to be flipped, some probability we'll call P. So if you want to send the message 010110, you might, on the other end of your channel, get 010100, right? And maybe that's the difference between like your video looking crystal clear or there being a weird pixel that's the wrong color or something. And you want to fix that. So what you do is you can encode into an error correcting code. So here on the top, I have a simple code I'll explain, where you have some message 01, where I've underlined the first bit of information, how you can follow it through the process. And then I encode it into 000111. I now send it through my noisy channel, and one bit experiences a bit flip, right? So now I get 010111. But crucially, if the person on the other end, my receiver, knows what code I used to code it, they can figure out that he probably meant 01, right? And they can actually be robust to a single error in our message. So an error code is a scheme that takes k bits of information and stores it in the data held by n bits, such that, so for example, this example, I have stored 2 bits of information in 6 bits of physical, physical bits that have been transferred. And that redundancy allows me to figure out what went wrong by kind of isolating what was likely to have happened. So you are always making an assumption, if things go wrong, you don't know if, for example, if 2 things went wrong, if instead of, maybe my message was 111, and I had this bit and this bit fail. The decoder doesn't know that, but it assumes that the more likely thing happened, hopefully our probability of failure is less than 50%, and it makes an assumption and makes a correction. And if it does that correctly, we can see some improvements. So the code I'm going to talk about today is the 3-bit repetition code. It's the simplest classical error correcting code. And as I mentioned, it takes 0 to 000 and 1 to 111. So there are now 6 other states that can happen, right? And I'll put this dividing line here to show where you would round or where you would pull states back to. So let's say I received the state 100. Well, one of 2 things has happened. Either the sender sent me 000 and the first bit failed, or they sent 111 and the second bit failed and the third bit failed. So, there's 2 pathways here, but they're both much less likely than this one here, assuming that our channel is even reasonably good. So using this, we assume we had followed this blue path and we just, revert back. We say, okay, 100, we're going to call that 000 and move on. And when you do this, you can see pretty significant improvements. So in this plot, I have on the x-axis the physical error rate, so P. Remember, we're going to assume P is less than 0.5 for the case of error correction. And then on the y-axis, I have this logical x error rate. So this is the chance that you misinterpret what happened. And then these different curves are different levels of redundancy. So I was talking about the 3-bit repetition code. However, you could use 13 bits instead. You could repeat 0 to 0000000000000. Yeah, that's 13. But you can do as many as you want. And as you do that, you can be more and more robust. So as you can see, the 13-bit code can make a 25% error rate still look really good, whereas the 3-bit code struggles. And that's because the less redundancy you have, the less confidence you have that no errors have occurred, right? And this is what we're sort of planning on doing with classical quantum error too, right? So the bigger code you have, the more error you can suppress. And so a big goal of ours is to make really large systems such that we can implement huge error correcting codes. And these codes are going to make error rates, as low as we want, 10 to the minus 10, et cetera. And then, yeah, so note also that above 0.5, things start to go really bad. This is called the threshold of a code. It's the distance at which increasing the size of your code improves things. If your error rate is really, really bad, making it bigger makes things worse because you have like more chances to fail essentially. But for our systems, we're pretty comfortably below 0.5. And then for the quantum's case, a big thing we're trying to do is push towards being below the threshold of our quantum reckoning codes, which are much lower than 0.5. Thresholds of quantum codes are much smaller because the problem is much more difficult, as I'll talk to you about sort of soon. But quickly, I want to just show you the implementation again, because I think this workflow is really important for us understanding how these things work, right? So first, we encode a message. We take 0 to 0, 0, 0, 1 to 1, 1, 1. Then we apply a noisy channel. And then the other person needs to know the same encoding, right? They need to be able to invert this encoding. If I don't tell them what I used, I could very well use 0 goes to 1, 0, 1, and 1 goes to 0, 1, 0. And that's also a valid encoding. They need to know exactly which encoding I used in order for them to be able to figure out what happened, right? So essentially, this is some sort of like, they have some classical information that tells them this is what this he's doing. I do it on my end, and they can use that to guess what happened on there. However, the key thing to see is that I have to look at these qubits, these bits directly. And so that's not allowed in a quantum system, right? As I've talked about today, measuring qubits collapses their waveform, right? So you damage your input, your state, by measuring it. So in a classical case, we're passing messages. So it's fine. You can destroy your state at the end once you know what the message is because you have the message. But our quantum computers are having noise happen during the middle of a computation. If I have some crazy entangled superimposed state, and then I measure it in order to understand if any errors happened, and I break the state, well, then I can't continue doing a computation with it. So our algorithms require no measurements to happen on the qubits during the application of the algorithm. And that means that we have to be really clever with how we figure out what errors have happened. So we need to find a way of identifying errors in our system without measuring the bits directly. And to do this, we use tests called stabilizers. So these are called stabilizer codes. And essentially what they do is you define a series of tests or constraints in your system such that your code words, 0, 0, 0, and 1, 1, 1 in the previous example, will pass both of your tests, while your states that have errors will not. And then you can see which things have failed in order to sort of guess at which qubits have had an error happen to them. So by analyzing which tests failed, we can identify what's going on. And then here on the bottom, I have written out the repetition code, that code I showed you earlier, 0, 0, 0 versus 1, 1, 1, in terms of stabilizers, so in terms of these tests. So what these orange bars are, they're labeled ZZ, is they essentially check whether this bit and this bit agree. And this guy is going to check if this bit and this bit agree. So 0, 0 and 1, 1 will both pass this particular test, whereas 0, 1 and 1, 0 will not. And the same thing is true here. So on our quantum computers, we can actually measure things like this without damaging the actual state 0 plus 1 or whatever that you have on this qubit. And so as long as both code words pass, we're actually okay. So let's understand again this sort of idea with our very simple toy example from earlier, right? So any classical code can also be thought about in this way. It's just you wouldn't want to because you have you can just look at the qubits directly, or the bits. But these green lines now and these red lines show what the stabilizer outcomes are for these particular bit strings. So if you have 0, 0, 0, well, your first two bits agree. So this stabilizer is happy, green. And these second two bits agree. So this guy's also green. However, in our 1, 0, 0 state from earlier, these two do not match. And so that stabilizer is going to light up. It's going to say, hey, something went wrong somewhere here. And what we can do is we can isolate, okay, well, this qubit in the middle talks to both of these. So if only this guy is saying something went wrong, chances are the leftmost qubit was the one that failed. And that's sort of what we'll do. So if I see red, green, or if I see, the second stabilizer says nothing went wrong, but the first one says something did go wrong, well, I think that this leftmost qubit that only this stabilizer sees is the one that has a problem. And so in this example, the only error that can happen is X. And so I will apply an X gate to this first qubit, flipping it from 0 to 1 or 1 to 0. And in this case, that'll take 1, 0, 0 back to 0, 0, 0. However, what you notice is that there's another state, 0, 1, 1, that also has the exact same stabilizer outcomes, right? And that's because, well, the same thing has happened. There's been a failure on the first qubit. So by applying this X gate, I would take 1, 0, 0 to 0, 0, 0, and simultaneously, I would have taken 0, 1, 1 to 1, 1, 1. So I actually don't know which state I'm correcting to. I don't know if the state I've now fixed was fixed to a 0 state or to a 1 state. I just know that I've fixed what I think went wrong. And this is what error correction is all about, right? So for example, if you had two things fail, you'd be in either 1, 0, 1 or 0, 1, 0. Both of those are fixed the exact same way by applying an X gate to this middle qubit, right? And that's what these algorithms do. They're essentially ways for a computer to identify what went wrong and correct it without knowing what state, without telling you what state that computer is holding. And that way, your superpositions are intact, your logical information is all protected, and your quantum computer can continue with whatever it was doing with that error now fixed. So the last thing I want to show you guys is a quantum error model, so we can translate this into a quantum error code. So as I mentioned earlier, we have a much richer set of states. We have this sphere instead of these 2 points. And so we have a larger set of possible errors. So we have bit flips, take 0 to 1 and 1 to 0. And we also have phase flips, take 0 plus 1 to 1, 0 minus 1, right? So this is basically just like a relative phase between 2 states. This is states flipping. So we need to catch both these errors. And that ends up with us having to need 2 types of stabilizers. So without getting too much of the math, essentially I'm going to make it all colors, right? And we're going to look at these things in terms of graphical diagrams. So they're going to be orange errors and blue errors, and there'll be orange stabilizers and blue stabilizers. And blue stabilizers will catch orange errors, and orange stabilizers will catch blue errors. Great. So by doing that, we can now look at this quantum error code, which is called the rotated surface code. So the surface code is one of the most popular error codes right now. It's what we at Google study and intend to use for our systems. And essentially, you can think of it as a checkerboard. So this is the smallest version of it. It is a 3x3 version. So you have this checkerboard pattern in the middle, and you have this boundary that just looks a bit different. As you scaled it up, you would need a larger checkerboard, and then your boundary would look sort of similar to this. So on this system, in this diagram, the white circles are the qubits that are actually going to store the information. And these orange and blue circles are qubits that are going to measure these stabilizers and help with sort of the error correcting code storing stuff or figuring out things. And as mentioned, these orange rectangles will catch bit flips, and these blue rectangles and lines will catch phase flip errors. So this blue rectangle here is going to check if any phase errors happened on qubit 0, 1, 3, or 4. Oh. This orange rectangle will see if any bit flip errors have happened on 1, 2, 4, or 5, and so on. And what we can do is we can figure out where errors have occurred based purely on this, what's happened. Oh, sorry, there's a question. How do you tell if there's a failure? What does it look like? So a failure, yes, that's perfect. So I'll go to the next slide and we can sort of figure it out together. So let's imagine, just look at just these red circles, right? So let's say I measure my 8 stabilizer outcomes. So these 8 colored circles, and just this one right here lights up. So I'm showing by this red circle here. So that means that I'm going to measure a bit string, which is going to be the outcomes of these 8 colored circles. And I'm going to get, 0, 0, 0, 1, 0, 0, 0, 0. So I know this guy lit up. And I need to figure out what happened as a result. Well, I know that blue errors make this guy light up. And if a blue error had happened here, 15 would also lit up. And if a blue error happened here, 13 would also lit up. So my guess is that either 1 or 2 have had an error occurred. And due to the structure of this code, in fact, these 2 errors are equivalent. So I can just correct this corner one and it'll work out. But these 2 are essentially equivalent because they're related by the same thing here. That's a bit above the level of this particular talk, but suffice to say, we can identify where the error was. Similarly here, let's say these 2 lit up. Well, then the most likely that happened was a single failure occurred here, which caused them both to break. However, note that could be wrong. This error could have occurred and this error could have occurred. And then we would have been incorrect. We'd have actually made the wrong assumption and our code would have failed. So as you go bigger and bigger, it's harder to fail, harder to fool yourself, but that's kind of the deal. And then what these errors actually look like is, just these outcomes and these stabilizers failing. So when I'm applying error correction on our computer at Google, I am pulling in bit strings over and over again. And I've got some code that analyzes this bit string of these outcomes and waits until there's a 1 somewhere, right? So it waits until some failure has occurred. And then it's like, wait, there's something that happened here. What happened? And it goes, and then it says like, okay, these 3 things have failed. I think that this error occurred. And then I could like correct that error and then continue going on. And then what's the physical? Are they physical? Yeah, so the physicalness of the stabilizers are, let's see, what's this? Yeah, so the stabilizers are essentially, yeah, you can think of them as like physical objects, like the state that we are preparing is constrained by the stabilizers we are planning on using in our code. And, but they aren't like, they're physical, not like, anything we do on our system is a Hamiltonian, is, some laser or in some pulse on a resonator. But they are not like, how to say this? Like when we apply a different code, we could change the code and do different things to our qubits. But they are a physical interaction between our qubits and another qubit, which we then measure, right? So what we're essentially doing is we prepared some state, which is a physical, state. Some error occurs, and then we use these stabilizers to map an error over here to the states of these 2 nearest neighbor things, measure these nearest neighbors, and then we know what error has physically occurred in our system, and then we correct that physical error. So there are physical things happening, and these stabilizers have physical meaning in terms of the particular states we are storing. And then, yes, so most of the time stabilizers are just poly operators. So these orange ones are ZZ type, and these X stabilizers, for example, this one here is X0, X1, X3, X4. But yeah, normally stabilizers are poly operators, and that's because we want to create this commuting set, and poly operators are a very nice way of doing that. Yeah, there is some research being done. I mean, this is more of a PhD. I was worried about this, but people have considered other setups, but they tend to be a lot more complicated, and we aren't yet sure if they're worth the extra complexity. So with that, I want to wrap up with enough time to maybe have questions. I think I've failed that. But as a summary, quantum computers are powerful tools that outperform classical computers on some tasks. Most of the applications that are useful involve simulating quantum systems in physics or chemistry. And we will need to see significant improvements in computational power before most applications are within reach. And then I have some resources here. So this textbook, I mean, you guys might know this already, but Quantum Information and Quantum Computation by Nielsen and Chuang is probably the canonical textbook in our field. So if you're interested and you have some linear algebra background, it teaches you all the quantum you need to know from linear. So if you're interested in this kind of stuff as a high schooler, you should try to go and learn linear algebra anyway. It's like going to be the most useful math you could learn probably at the next level. And then, yes, this textbook will explain everything else. There's also a great video series from Umesh Vazirani, who's a professor at Berkeley. And that also is a great resource if you're interested in these kind of things. And then we just recently released a new website, quantumai.google. And we also have a bunch of educational tools there, as well as a roadmap to what we plan on doing in the next 10 years. So if you're interested in this field and you want to see what our plan is, we have a lot of our plan published publicly, and you can go and follow along and see what things we can do and when we hope to do them by. And then, yeah, this is a picture of the team. Obviously, we haven't been in person in a while, so this is from 2019, I believe, before I got there. But there are real people working here. These are the faces behind what we're doing. The team is much larger now, but yeah, this is in Santa Barbara, where most of our hardware is held. Yeah, so thanks. I'm happy to hang out for some questions if people want to. I don't know if you guys have a schedule, but yeah.
Yeah, you can say, if anyone has any questions, you guys can ask them.
Yes, so now y'all are free to resume your hacking, but right now, if anyone has any questions for Dripto, they can stay and ask. Also, Dripto, if anyone has any questions after, how can they reach you?
My email is dripto@google. Benefit of having a weird name, you can generally snag it. So yeah, I can just type into chat, but it's just
that would be great. Yeah, so if you have any questions and you can't ask them right now, you can just email them to him. Jamie has a question though.
Yeah, perfect. Have quantum American codes been implemented on real quantum devices? Yeah, so there's an archive paper that I wrote during my PhD that you can look up, where we did one on an ion trap system, and then Honeywell has also implemented one, and then we also have implemented Eric codes. So we have a paper on repetition codes, and we are, I think everyone in the field right now is working towards that as their next milestone. So if you check out Quantum AI at Google, we have our milestones written there, and our next one is full error correction of the code actually I showed you earlier, and trying to show that these things can work and show that we can improve reliability and basically build towards having a single really high fidelity logical qubit and then scaling that to multiple. And what do I think about Google's quantum computing claims? So yeah, let's see. I'm not sure what exactly you mean by what do you think about them. I think that, so I wasn't at Google when that happened, so this is more of an outsider perspective that's now an insider, I guess. But my take is that nobody at Google or anywhere is claiming that the particular problem that they solved was like world changing or anything. This was not like people were trying to solve this problem before quantum computing existed. What I think is very useful in showing that we are no longer in the realm of toys, which is to say that if I have a 5-qubit device, even a perfect 5-qubit device, I could simulate that on a piece of paper, right? Like given some time to do some matrix multiplication, that is a solvable problem. Like a 3-qubit device is 8x8 matrix multiplication, right? So if you have a 5-qubit chip, no matter how strong it is, no matter how good the qubits are, it is going to be worse than a classical computer with MATLAB on it that can do some 32x32 matrix multiplication. The interesting thing about the quantum supremacy experiment is that it shows that we are able to now create systems which can have signals that a classical computer would struggle to replicate. However, it isn't just about having those a powerful object, right? Like that's a problem that's perfectly picked to be easier on a classical computer, a quantum computer than a classical one. But I think it shows that we are now working with devices that have actual real life, impact, and are starting to get to the point where they can do useful things. So yeah, that's my thought on it. It's not, I don't think it's necessarily that this claim is that like that result means that, throw out your laptop, we're done. It's just that claim means we're now working with, actual interesting objects that are no longer worse than my laptop or an SSH connection to a cluster. But yeah. Where can I learn about quantum American codes like repetition codes, Shor, Steen, etc.? Yeah, so I think that the best place to start in terms of like easier intros are actually in Nielsen and Chuang. So this book is now 14 years old or so it's not like super cutting edge, but things like Steen code, Shor code, CSS, etc. are in that book. And so you can learn the basics there. Also, depending on your math level, John Preskill, the professor at Caltech, has some really good lecture notes, and he's a pioneer of error correction codes. And so he has some great lecture notes that do build up on it. But I would definitely start with QIQC. Yeah, the ebook, I think you can find it. Yeah, and then, Quantum Computing by Nielsen, he does a lot of really good work on quantum education. There's a lot of really good resources out there for quantum computing. I think that's a great side effect of people being really excited about it. So like, I didn't touch source code, but I know there's a great YouTube video that like explains like a lot of it in relatively accessible language. And yeah, if you're interested in error correction, I think that the best place to start with error correction would be either, depending on if you're like a more math person or more of a physics person, or if you're more interested in classical or quantum stuff. Classical error correction, I think, is easier to understand the basics of. And then quantum error correction kind of was built by classical error correction theorists, right? Like CSS, Calderbank. I mean, I've worked with Calderbank. He's a classical error correction guy who does quantum as well. So I think you can learn it through that pathway as well, and it's very fruitful. But yeah. Anything else? And then feel free to email me as well. I can help you out later if there's any questions.
Okay, so if it looks like
All
there's
right.
no more questions, yeah, Dripto, thank you so much for coming. And everyone, if you didn't get his email, it is dripto@google.com, I think, right?
Yeah.
Dripto@google.com.
I
Yeah.
can go to the front to have my name out. Here
Yes.
it's
Yep.
just this.
Yes, make sure to email him if you have any more questions. And I really appreciate you coming in. And for everyone else who's still here, get back to hacking, and we'll see you in a few hours with Danica. Okay, bye everyone.
Yeah. Good luck.